the dispatcher latency. If we consider the dispatcher latency here, it's much more complicated. So to simplify, to focus on the algorithm, so we are going to use without the dispatcher latency, we'd like to minimize the response time, and also we'd like to minimize the wait time. So this is our goal of the CPU scheduling. Okay? So, idea of such the CPU scheduling is one more thing before we start. The CPU has, what is the CPU by the way?
Is the arithmetic logic unit, the LAU in the register.
Is the CPU is the device. So all the devices on your computer are I/O devices. CPU is one of them. CPU has an input and output. Then during that time, what happened? Mostly computation. It has based on the ALU, as you learned in your microprocessor class, it has a plus minus and there are number of defined operation, which is called what? Instruction. So instruction, if you take a look at instruction, most of them are related to what? Computation. What if I can find the read? I can find the write. This is read and write. But during when the CPU process the read instruction, write instruction, what they are doing? What the processor is doing? Nothing. Only send the signal to the I/O device, monitor device, mouse device, based on the signal, and the wait until response. So we can consider that there are two different jobs on your program. Roughly, one is I/O, another one is computation. So during the computation time, CPU can compute, so no problem. But during the I/O, the CPU cannot do any other job. So we try to utilize this time. So we can we can actually divide the CPU time like this. So CPU burst time means it's computation. Then the I/O burst time is the I/O wait. During that time, CPU cannot do anything, just wait. So we don't want to waste such an I/O wait. Instead, changing the process. That means I/O time. So that is the idea of CPU scheduling. We are going to maximize the CPU utilization by changing, by transiting the processor, one process to another processor. Specifically, those who need the computation part. Okay. So this is kind of the illustration of how the CPU scheduling is working in terms of the CPU burst time and the I/O burst time. So we are going to, this one is, let's see this one. So this one is better. So we have the I/O bounded job, okay? So at that time, actually CPU cannot do anything, just wait. So we are going to utilize this CPU time for another, the CPU bounded job. So this is the idea of the CPU scheduler. So let's start. So CPU, sometimes it's called the CPU scheduler, and also it's called the dispatcher. So what is a CPU scheduler? What is a dispatcher? If you are asked by your manager, why don't you implement the CPU scheduler or the enhance and make the new idea, create the new idea for the I/O scheduler, then how can you implement? It's a software program. It's a part of kernel operating system. So if you have a new idea, it's 10% better than the existing one. So you can replace the existing one by the new proposed one. But nowadays, not many. But 10, 20 years ago, in the operating system class, one of the most popular programming project is to implement the CPU scheduling algorithm. Then if you can enhance, you can publish the paper. So then, at that time, when? So just think about our real life. So during the Professor Lee's office hour, when does the transition time happen? Like the current process is done, the current student, the time is done, is terminating. Also, it's to take a long time. It's a maximum 50 minutes. So after 50 minutes, go back to wait. It's a second case. And also, IO wait. If there is a request to read the student file, we need to wait. So take the next the student. So third one. And also, if the secretary bring the student file, then we can select the next student also. So these are the cases of the flow. Switch from running to wait, and running to ready, and waiting to ready, and terminate. So for the cases, your CPU scheduler will be activated, which means operating system run your CPU scheduler, which means CPU scheduler might be a very important process. That is the reason some of the operating system use scheduler as the init process, the first process, most the important priority. So you can see the PS command, then the SCHED process is running. It's a scheduler program, and then so you can select the next processes. At this time, there are two types of the CPU scheduling algorithm. One is a preemptive, and another one is a non-preemptive. What is the dictionary meaning? In terms of the dictionary, what's the meaning of a preemptive and the non-preemptive? What are the difference? Preemptive is before and get back.
Oh.
Right? And on the other hand, the non-preemptive is not. So which means, if your process, if your scheduler is the preemptive, which means, so one more time, the advising time. So student need 1 hour. So to review the paper report, but it's only the 15 minutes for advice. So after 15 minutes, and wait again. And after 15 minutes, wait again. After 15 minutes, wait again. After 15 minutes, wait again. It can be restored. It can be restored the next. So that is called a preemptive, the algorithm. On the other hand, if your scheduler is non-preemptive means you cannot restore the state. Once start, should be end. So 1 hour. So this is a preemptive, the scheduling algorithm. So we are going to see both preemptive and non-preemptive, but you can easily guess. Nowadays, the modern operating system use preemptive or non-preemptive. Many of them, most of them are using preemptive scheduling algorithm. But also, we are going to see non-preemptive, the scheduling algorithm. So, as you can see, nowadays most of the operating system, including Windows, Mac OS, Linux, and Unix, they are using the preemptive scheduling algorithm. That makes sense because we can say the operating system concept and the algorithm are fighting with what? Fighting against from the limited resources. Yeah, so CPU is the really critical. Even though you are using the multiple processor and multi-core system, still limited resource. We need to schedule. At that time, if you are using non-preemptive only scheduler, so what if something very heavy job? So it takes a day, 24 hours, then none of the other process can get the CPU resources. So nowadays, most of the CPU scheduling is a preemptive. However, in this class, we are going to see the even non-preemptive. That is the easy to understand. Then we can extend to the non-preemptive.
In which cases non-preemptive will be beneficial?
So operating system is not only for the general purpose.
Oh,
So, yeah, sometimes embedded system, sometimes mission critical system, sometimes it's a single process operating system. At that time, it's a non-preemptive. Okay? But obviously, in case of a preemptive, there might be the issues, right? The race condition. So we will discuss the race condition, the synchronization problem in the next chapter. So what is the dispatcher? We already discussed. It's the schedule. Oh, so it's the previous slide. So this one is the, I think the somewhere. Oh, we do not have that slide. That I draw. The dispatcher is a process that actually select the process by watching the signal. So how does the operating system know whether I need to activate or not for the dispatcher? Because of the signal. Okay. So like the I/O signal. So if the device read the data from hard disk drive, the device controller, disk controller, send the signal to the operating system. Interrupt signal can be used. Then the dispatcher will be activated like that. But obviously it has the latency, but the dispatcher latency we will ignore to simplify the problem. However, in real life system, real life operating, definitely you need to consider such a dispatcher latency. So there are several criteria to judge whether my algorithm is good or not. So utilization, CPU utilization is 100 is the best one, CPU utilization. But if you have really 100% CPU utilization, it's too much busy. So your operating system will not work. So, but in our class, this chapter, we pursue each algorithm has 100% CPU utilization. But if you consider the dispatcher latency, it will be less than 100%. Throughput is the number of processes completed. So specifically, if your operating system focuses on the batch job, so who uses such a throughput? Think about the conveyor belt in the automobile industry. They only check how many cars are produced every day, right? They don't care response time or they don't care utilization. It's always running the conveyor belt. But they try to check the 1,000 a day or 2,000 a day. So that means it's a throughput. So throughput is one of the ways to judge how much the operating system is working. Especially this one is good for the batch job, the oriented operating system. However, this one, we don't know. Like for example, even though you process many transactions a day, but if each transaction has the delayed waiting time a lot, let's think about the stock market trading. Okay, so in stock market trading, batch job is not important. Instead, response time. First, the response time is more important. So when I click in the millisecond advance than other, I can gain. I can sell the stock, right? So at that time, the response time is more important. Response time. So sometimes it's not. This is time. This is the 0, 1, 2, 3, 4, 5. So, let me Okay, so first, this is a timeline. 0, 1, 2, 3, 4, 5, 6, 7, 8. This is the time. If process entered this one, okay? So right now it's in the ready queue. Then the time 3 is selected. Okay? So it's a new state. So 3 to 5. And go back to the, at this time, the ready again. So this is the new, this is not new, this is running. This is a running, and then wait again. And select it again, run, and terminate. Okay, so this is the one example for processor 0. So at this time, question, what is the response time in this case? How long this process has been waiting for the first response? How long? It's a 0 to what? 3. So it wait the 3 time slot. Okay? However, this is not waiting time. This is what? Response time. So response time is the starting to until the first response. So this one. However, this process has been waiting what? 1 time, 2 time slot here. So what is the waiting time? So response time is 3. What is the total waiting time? 1, 2, 3, 4, 5. So 3 plus 2. So 5 is the waiting time. So don't be confused. Response time and waiting time are different. Waiting time is the total waiting time. However, response time is the only first waiting time until the first response. So, which one is more important for the stock market trading? Waiting time or the response time? Response time is important. If somebody enter the first, then you will get the priority. It doesn't matter how long wait during the transaction, but the first response time. So response time is good. However, waiting time is also important when you consider how fast your transaction is. Because total transaction time is beginning to end 8. Right? Only CPU time is 3, but the wait is 8. So depending on the objective, the goal of your operating system, you need to consider the response time sometimes. You need to consider waiting time. And throughput is until this time, how many processes are completed. In this case, only 1. If there is another process, P1, so P1 is terminated, and the 2. Throughput is number of processes. Okay? And turnaround time. There is one more turnaround time. So turnaround time is the beginning to the end. So, which means it starts from here and end here. Turnaround time is the total time. That includes the CPU time as well as the waiting time. It's 8 time slot. So turnaround time is the total amount of time to complete the process. If you understand this, then we are going to mostly use response time and the waiting time to judge, to decide which algorithm is better than the others, like that. And also, if you have the multiple process, like a P1, P2, P3, you need to average. So we are going to use an average response time, average waiting time to judge the CPU scheduling algorithm. So that is the CPU utilization, turnaround time, throughput, turnaround time, waiting time, response time. But in this class, we are going to consider waiting time and response time for the kind of the rubric to judge the CPU scheduling algorithm. But we have multiple processes, so we are going to average it. So average waiting time and average response time. Then our goal is maximize the CPU utilization, maximize throughput in terms of waiting time and the response time. Definitely minimize the waiting time, minimize the response time. These are the algorithms we are going to discuss.
Wait, you said minimize the response time?
Yes. So which one is better? If you when you buy the Google stock, so you click, then the response time is a day. Well, 1 second. Which one is better?
Okay.
1 second is definitely better.
Okay.
Even though it takes a day later, but your transaction is started, so you have the priority. So that is the reason the most of website they focus on the less than 7-second response time. Otherwise, people leave your website, right? If response time is too long. In general, rule of thumb is a 7-second waiting time. Okay. So response time, I mean. Okay, so these are the list of algorithms that we are going to see. I'm going to explain all these algorithms within a minute. Within a minute, I'm going to explain all this. You know the first come first serve, right?
Yeah.
So done. But some of the students in the waiting line, so they need only signature. So we can give the priority to those signatures. That is the jury's job first. Some of the process is very quickly done. So we are going to select such a process first. So that makes sense. And not always such a jury's job remaining, because it takes time. So I met you, but you need 16 minutes. 16 minutes. But you already done the 15 minutes. Remaining time is 1 minute. So I can give the priority. Remaining job. Remaining time first. So that is the jury's remaining time.
Professor, how do you calculate the remaining time of a process?
We will see. Okay? We will see. That is one of the main problems of
Yes.
that. Okay? But nowadays we have very nice machine learning algorithm to estimate. So that's a really good question. That is the main problem of the CPU scheduling algorithm nowadays. But we can give the priority. So you have the first priority. Have the lowest priority. Always, even though you are late, because you reserve the time, so you can get the CPU research. You can be the professor. Priority. We don't like such a thing. Just take time. That is a fair round robin, right? Every 10 minutes, you then go back round robin. 10 minutes, 10 minutes, 10 minutes. So that is round robin. To be fair, and obviously this one gives the best algorithm in terms of what?
Waiting time.
Response time.
Oh, because you.
Yes. You may wait later, but at least you will get the chance to meet. Right? So this is round robin. These are only the one queue for waiting. Can we have the multiple queue? Like I have the TA1 and the TA2. So if you have the easy problem, TA2. If he or she cannot solve the problem, TA1. If they cannot solve the problem, then you can meet. So kind of how many queue? Multiple queue. So we can do the same thing, multi-level queue, like that. Multi-level feedback queue is the first queue give the feedback. These guys is really don't understand anything than the different priority. Okay, there's a feedback, and then the TA1 take care, or directly the professor take care such a student, like that. And for example, TA2 is time of matter. So TA1 can take care, or I can take care of this student. So depending on the output of or response of the first queue, then we will give the different priority to the queue. So that is a multi-level feedback queue, which means each queue has a different algorithm. So I'm done. Okay. So in real life operating system, they are using actually the hybrid. So they are not using only the first come first serve. They are using the mixed hybrid approach. So first we are going to start a lot of the algorithm used in the operating system is based on the first come first serve. Why? Why?
I mean, the faster you complete a process, the more you have to work with the other one. So the first process that come in is the first one that should leave.
Easy.
Yeah.
It is just
Easy to implement. And also, because the operating system already provides a queue data structure as a part of operating system. As we discussed, one part of operating system is the data structure. They provide a stack, they provide a queue, and so message queue. We can use the message queue on the memory. We don't have to implement a queue, right? For communication, we can just use the system library, the message queue, or share the library like that. So queue is easy, and also relatively most fair, because it's a first come first serve. So it's a relatively fair. I'm saying relatively and reasonably fair, not always. But if you go back to this algorithm, we can understand that such an algorithm, all of them are based on priority. So, for example, first come first, what is the priority?
it's higher the sooner you come.
When? So, arrival time.
Yeah.
And what about this one?
Job.
Size of job, heavy or light. And this one, shortest remaining
Remaining.
is the priority. This one is explicitly assigned the priority. Windows use this one, and many of the operating systems use the priority. So, for example, Windows priority has a 0 to 15 priority. If you remember Task Manager, you can change the priority of the process. Right? Right click, then the normal, and high is the priority. And the low is the priority, but there's a warning sign always. Do not change it. They're like that. Because then they mess up the scheduling algorithm, but they will not mess up your operating system, even though you change it. Okay? So, and the round robin,
They all have the same priority.
yes. And multi-level queue, each level. I said queue is the priority. So, lower priority, queue. And the highest priority, queue. And this one is the different types of queue. So we can understand it's not only for the scheduling algorithm, many of the algorithms used in the computer system, we can think about what is the most important criteria, or what is the priority. Then we can focus on that priority to address such a problem in the computer science and data structure and algorithm. So this is the typical example. So we are going to start with the first come, first serve, the scheduling algorithm. Here, there are several notations that we are going to use. We are going to use this kind of chart. So this is along the time. Okay, 0 to 30 means it's a CPU time. We assume the first is one CPU, one thread, one core. Okay. So if we have a multi-core, we will discuss later. Okay. Then this one is the CPU time. There is no overhead for the context switch. No dispatcher transfer. It's right away. There is no waste of time to simplify the problem. But in real life system, obviously there is such a time there. Then when we see this, there's no meaning of the width. It's just the illustration purpose for better readability. So this one means P1 start here. Start means running. Selected from the wait queue, ready queue. Then running 24. There's no specific unit of the time. I'm going to say this is a slot. But usually CPU time is a millisecond level. Okay? it's a millisecond level take time. But in our class, so to simplify, we are not going to use the specific the unit. But this is just a time slot. Then P1 is done. This one is done. Then the P2 is selected. Take the 3 time slot and then followed by P3 like that. At this time, we need change it. I think that, yes, then the student can watch this. So I strongly suggest this one is really easy. So let me first explain this one. This is called the process list, process table. So it tells all the information about the process. Question: where can you get such information?
On the queue.
Q?
Task manager?
We learn PCB,
Yeah.
process
Then
control.
on the queue, but yeah.
Then Q has the number of PCB.
Yes.
Okay. So process one. So information you can find the P1, the PCB. It has the CPU burst time. It has the process ID. It has the process name. It has everything. But here is a simplified process table. Okay. What we need is a P1 process name. Okay. And burst time is P1 need a 24 time slot, CPU time slot. P2 need 3 time slot. P3 need 3 time slot. Then this is the queue. First in, first out. So oldest one is the youngest one. No, opposite. It's the enter the first thing. Okay. Top means it's the first thing. Then the P1 will be selected like that. But from now on, whenever we discuss about such a CPU scheduling algorithm, let me illustrate again. So this one. So this is a new. This is a ready. This is the running. This is a wait. This is the terminate. So to simplify, we are not going to consider the I/O wait. Okay, only we are going to consider the CPU burst time. So in advanced operating system level, you are able to consider such I/O wait also. But you need more information in addition to this one. So this means, this will be this. If this one is a non-preemptive, we don't need this. Non-preemptive means once start, it will be terminated. So in case of preemptive, it will go back. So we are going to manage the definitely ready queue. So please manage the ready queue. This is the first in, and like the in, out, ready queue. And running. How many running? Only one. So you'd better manage this. Then follow me. So first, process one is alive, right? This time, process one is alive with the time 24. Then process two is alive, and 3. Process 3 is alive, the CPU time 3. So this is the ready queue, and this is the running. So first, which one will be selected?
P1.
The P1, because it's the first in, first out. So ready queue, we will take the P1, 24. So this is the current status when time is 0. So you need to manage also time. So time is 0. And time 0 is like this one. So for illustrating purpose, we are going to use this kind of the timeline. This is called the Gantt chart. Gantt chart. So Gantt chart is along the time Each process is taking CPU resource. It's a very simple chart. So P, let me draw. It's really the same, but I will show how to draw the Gantt chart. P0 here. So we can select the P1. So P1 is selected. P1 is selected. Then this is a non-preemptive. So first come, first up is a non-preemptive, which means once it is selected, it should be terminated. How long? 24. So 1, 2, 3, 4, and 24 time slot. P1 take the up to 24. So this is 24. Then time, so 24. What happened? This one will be terminated. So if you want, you can manage one more data structure, terminated process. So it does have to be the P1 is terminated. Then next, CPU scheduler select next process. First come, first serve. So P2 will be selected for time slot 3. Okay, then you can draw the Gantt chart. P2. How long?
3.
3. So this is the 27. Right now, current time slot is 27. Then this one will be terminated and P2 like this. What is the time? 27. Then select the next one, P3. So P3 will be selected from the ready queue and P3 with the time slot 3. Then P3 will be selected up to 3. So that is a 30 like this. So that this one finally empty and the P3 will be terminated. So this is the status when time is the 30. Okay, so that is done. Then that's it. We need to evaluate. We need to judge how much fast or not using what? Waiting time and response time. First, waiting time. So P1. How long does P1 wait?
0. P1 0 wait.
0. It's selected right away, right? P1 is selected right away, so 0 time. What about the P2?
24.
P2 is started here, but 24. So it's a 24. P3,
27.
27. So average waiting time is add up 51 divided by 3. So it's a total 27. So 27 average waiting time. What about the response time?
Response time?
First response, P1,
0.
0. P2,
24.
24. P3,
27.
27. Same as waiting time. So this is one idea. If non-preemptive case, non-preemptive means once you start, then terminate. There is no waiting time in the middle. So which means average waiting time and the average response time should be same in non-preemptive case. So this is the easiest one. So it's for your better understanding, I have used the first come first serve non-preemptive case. Okay. Then when you see this algorithm, can you find any issue or the problem?
I mean, you can have a process that eats both the resources, and you can. The second process has to wait 24 units.
Right.
That's too
Yeah. They start at the same time, but we cannot line up the same priority. So P1 is selected, then P2, P3, right? Then P2 and P3 they should wait for long because of P1. So this is called the convoy effect. Convoy effect means if there's a long learning process, like to think about the advising time. the one PhD student, I need only signature. It takes just a second, but I should wait out. It happen a lot, right?
That's annoying, yeah.
Yeah. What if the professor just give a time for a second to sign, then everybody happy?
Yeah, that means the professor, it is better to start P2,
Yes.
then P3, and the last one P3, P1.
Yes. So that is the
P2 is the first come and shortest one.
yes. So what if we can arrival time
Yes.
is changed like the P2, P3, P1. Okay. That means the P2, P3, P1. This is 24. This is 3 and 3. Then Gantt chart obviously P2, P3, and P1. So if we calculate the average waiting time again, so from this the Gantt chart, so P1 wait how long? 6. Right? P2 wait 0. P3 wait
3,
3. So total 9
Nine.
over 3,
3.
3. The previous one 27. This one 3. So which one is better? Obviously this one is much better.
Yeah,
By changing only order of P1.
yeah.
Right? So this is called the combo effect. We need to address such a combo effect. How?
Convoy effect.
How?
Shortest process.
So I take into account burst time.
First time. So not only just arrival time, we can consider the burst time. So that is later it's called the tourist job first. So before that, we are going to see we assume the last time P1, P2, P3 arrive at the same time, right? But what if their arrival time is different? How can you get the arrival time? Arrival time of what? So ready queue.
Yeah.
Okay, ready queue. So in your PCB, you should manage when the process is created, when it's selected. All CPU scheduling information will be managed on your PCB. That's the reason accessing and managing the PCB is very important. So actually, there is much more information can be managed in the PCB if you take a look at the header file information on the Linux. We have a slide, but I didn't explain, but if you take a look at it, it has all the information. But this process table has what? Arrival time and CPU burst time. So more information about the arrival time. At this time, if we draw the Gantt chart using first come first serve, it's the same as the previous one, the first one, right? P1, P2, P3. If we calculate the waiting time, it may be different because their arrival time is different. Let's quickly calculate the waiting time. P1 waiting time obviously is 0, right? P2 waiting time is starting 24, but it arrival time 1, okay? So if I ask you to manage the ready queue and running and the terminate and the time. So this is a good example to see how the data structure will be changed along the time. At time 0, what happened? P1 is alive with the CPU burst time 24. Okay? So it's a time 0. Then at time 1 is a P1 is selected 24. The time 1 P2 is alive. Like that. Okay? You need to manage the arrival time. Here, 0,1, 1,3. Then during the time P3 arrive at time 2, so time 2, P1 still there, right? Because it's non-preemptive. And P3 arrived like that. Then nothing happened. If something happened, you can keep changing. Then the time 24, this one running queue is empty. empty because the P1 is retired, terminated. Then this time the dispatcher select the first one. So P2 is selected, and like this. Then nothing happened, and P3 will be selected, and time 27. And this one is terminated, P2, and P3 is selected, and like that. And time 30, everything is done, P3, and like that. Then, if you calculate the average waiting time, P1, obviously 0, P2, 24, minus 1, arrival time. P3, 27, minus 2. So this is 23, this is 25, it's total 45, divided by 3, it's a 15. It's a 15? Or it's a 8? 16. 16. Okay. However, if we change the arrival time, like the 0, 1, 2, we can follow the same thing, then calculate the average waiting time, it will be 2. So which one is better, 2 and 3? Definitely this one is better. So we need to address such a convoy effect for the first come, first serve. How can we address? Instead of arrival time, we are going to focus on this one, the CPU burst time. So that is called the Heuris drop first. This might be the last one today. So drop means sometimes in operating system or the computer system and computer science, drop means what? Process. So we interchangeably use. So Heuris drop means Heuris CPU burst time. Okay, CPU burst time. So why not select the processor from the ready queue? So P1 has the arrival time 1 and need 12 the CPU time. Process 2 is arrival 2, but 3 like that. We are going to take a look at that time when dispatcher is activated. At that time, take a look at this one. This is the priority. Okay, this is called the Heuris job first. So this is the example. So ready queue is right now P1 6, P2 8, P3 7, P4 3. This is a ready queue, so we can manage the running and terminating and time. So at time 0, this is time 0. So 6, 8, 7, 3. Which one will be selected? Which one is the shortest job? P4 is the shortest.
Yes.
So P4 is selected. So this one is, yeah. Then this is the non-preemptive. Still non-preemptive, which means it will be completed. So P4 will be completed when time is 3. This. So current time is 3. Current time is 3. At this time, which one will be selected?
P1.
6. So P1 will be selected. We are going to consider the process that is the shortest job. So P1 is selected. Then the P1 need what? The 6 time slot. So 9. At time 9, P1 is terminated. Then we need to select the one of them. That is a P3. So P3 takes the 7 time slot at time 16.
Yes.
Then P2 will be selected finally. And P3 and P2. Then time 24, it will be completed. Let's calculate the average waiting time. P4, obviously 0. P1, 3. P3, 9. P to 16. So if you add up 28, right? Then 28 divided by how many process? 4. So 7 average waiting time. Still, there is no waiting time in the middle, which means response time is the same thing. So average response time is the same as this one. So this is the optimal. Optimal in terms of what? Waiting time. It's optimal in terms of waiting time. The reason why I am showing that this one is, if you are asked to implement, how can you start the program to implement the schedule? Here is job first, or any scheduling algorithm. How do you start? How do you start? How can you start? Let's think about the C program, or even Java program. So any program language, but how can you start? You need to define much.
Define 3 queues.
PCB data structure. Or if we are using object-oriented program, PCB can be object, then create on the instantiate on the memory using your design, the PCB. In this PCB object may have the data, number of data, and also like the read, write, add, and something like the method. Then what will be the next?
You need to define your queues.
Ready queue. You need to create the ready queue in your program. And also you need to have the running. It can be state, but you'd better have the separate data structure for running. Then you need to manage which one will be, which one, the terminated, and the current time slot. While and keep the checking the such a thing. So because it's a kind of very high level data structure. So you'd better understand the scheduling algorithm in terms of data structure. Then it's much easier. The simple one, this algorithm is not the rocket science. Most of algorithm, as I said, is less than a minute to explain. But you should be able to implement after this. Okay? So also this kind of the scheduling, sometimes many of the algorithms used and discussed in this operating system class can be used for your application programmers. In your application later, you are going to get a job as a software engineer, developer. Then I don't need such a scheduling. Sometimes you, in your application level, you should have the scheduling. Like if you have the many transactions from so you are working for the hotels.com. So there is very nice deal, then there are a lot of transactions. So you need to manage such a queue and schedule which one will be selected and so on. And also synchronization problem, definitely. Many of the time, program languages provide their library for scheduling or especially the synchronization. You may not realize, but when I met one time, Price.com, I met the CTO of the Price.com. So I asked him what is the first criteria when you hire your employee. Then it doesn't take even the second. He answered the candidate should understand the synchronization problem. Why? Because the Price.com, they do not have the travel agent. Instead, they are accessing many different, even heterogeneous, the agent or the source, like the MTA or the Amtrak and the airplane. You need to manage because eventually their data are stored in their database. Definitely, it has the synchronization issue. Okay, which one reserved and before payment, and who will get such an opportunity for the nice deal or the hot deal, right? So that time, the managing such a shared data very important. So operating system is not only for the operating system. These kind of algorithm eventually used in what? Your application level. So technical interview, when you apply the job as a software engineer, the first thing you need to do is you need to show and you need to prove the programming skill. Unfortunately, that is rarely happen, the most of cases. And then what they are asking is some of the company, they just ask the question from the data structure textbook or the Googling the sample question, but the decent job or the IT company, the medium bigger size the company, they are asking their real problem. It's a simplified. So, for example, if they have something scheduling issue, they ask this kind of question. Why don't you implement? So you have the 10 data items, the that alive randomly. Then why don't you optimize the weight in terms of waiting time? They'll give the 30 minutes, and you can implement the code like that. Okay? So operating system is not just the operating system. It's the understanding the algorithm and data structure. Okay? So this is a good example. So I have used this one for the programming project before. The student liked this, but there are a lot of existing references for this. Okay, so this is the theory job. Problem.
I mean, it's not. I mean,
You already asked.
how to determine the time?
Yeah, this. Once when you start your process program, do you know how long it takes?
No.
Obviously not. But we can estimate, right? Based on what? Previous history. Like usually, for example, to start Windows, the Microsoft Word, it takes 10 seconds. So that is kind of the waiting time 10 seconds. It has been used 20 seconds like that. And also, you can actually estimate based on the last 3 seconds. If the CPU time is 10 and 8, 6, 4, depending on the time slot, what will be the next? It will not like this. Probably the 2 and the left. So based on the previous data, we can guess the next one. It's pretty much work, and there are a lot of algorithms to predict such a pattern. This is not changing or randomly. Okay? It's based on the previous data. So to do that, Kalman filtering, Monte Carlo, you heard about such the algorithm, the Markov model, so can be used to the estimate the CPU time. That is the first problem. And second, can you find any issues of this kind of shortest job? Obviously better than just a simple first come first serve. This one is just a kind of steady process table. What if there are incoming?
You have to reorder every time.
The order will be first because it's the queue. But we are going to select the
search.
person.
You
need to search,
you
right?
have to keep searching.
At that time, one problem is if the processor 5 is the CPU burst time, CPU 6 is 1, process 7 is 1. What about this process?
It never.
Never. This is called what? Starvation problem. So any priority-based algorithm, so we already discussed, our scheduling algorithms are considered as the priority-based. Any priority-based algorithm has the same problem, starvation. Do you remember how to address the starvation in your algorithm class?
CSFS.
Okay.
I mean, what you can do, you can also keep track of time.
Yeah, so for example, the students are waiting. Keep waiting because I need the 10 minutes for professor, but because of the other student who need the signature, I cannot get. Then you can promote. You can promote the priority, okay, which is called the aging. along the time, certain amount of time, if you wait and promote, then you can eventually get the chance. Any other issues? This is a preemptive,
Yes.
a non-preemptive
Non-preemptive.
once it starts. But what if the non-preemptive, a preemptive case, which means if there is a new process coming in, we need to run it again. So in the middle, eventually the CPU burst time will be reduced. But if you just consider the beginning of the CPU burst time, so it's not fair. So the problem is why not considering the remaining job? So we have the shortest remaining job first, later. So the shortest job first we already done. Then this is a non-preemptive case. Once the process starts, it will not be preemptive. So it should be terminated like that. But in case of preemptive, so at this time and time 0, CPU burst time 7. So at time 0, P1 definitely selected because ready queue only one process. Then the P2, there's new arrival of the process 2.
Yes.
Okay? At this time, what is the remaining job?
5.
5. But we do not use such a remaining job. It's still 7. Okay?
7.
Yeah. So which one will be selected? For this P2 will be selected. And time for the P3 is alive. And at this time, it's the CPU burst time is 1. So obviously this one will be selected. Then the P2. And the P4, when the P4 is alive, it will be selected because P1 has a 7. So also this is not fair, even though it's the preemptive. So we can consider remaining job instead of shortest job. Okay? So, I sort of passed the 5 minutes. So this is the last one. So how can we determine the CPU burst time? So that is the critical, but we have data. It's one of the function of operating system is journaling, which means you keep all the resource and how much used and which process are running. So you have such a journal data. Based on such a journal data, we are going to predict the CPU burst time. So there are a bunch of different process and the algorithm to predict. So, but this is one of the simplest using tau. So you can guess. You can see the next one is based on the previous one. You should have the threshold value, how much you consider the previous and how much for the current last one, like that. And eventually this one, the predict. So this is actually real, the data that predict. This one is the real and this is predicted. It's pretty much similar pattern. Okay, so that is the CPU scheduling. So we are going to continue the CPU scheduling the next class. Okay. Any questions? Any questions? Okay, so please keep working for the project 1. Okay. And don't forget to submit your homework to the Canvas if the due date is earlier than our class schedule. The BAMC, the GA will adjust the due date for the homework, but don't forget to submit the homework on time. Okay, thank you. We will see you on Wednesday.